Okay, we're going to wrap up this chapter here, which will again be the last one on the upcoming exam, which is 2 weeks from today. Yeah, so that is what's coming up. We've been talking chapter 15, I believe. And last time we got into KSP a little bit more. Remember, KSP is really, again, the solubility product, which is for our solid and really insoluble ionic compounds, where we always write solids on the left. And again, it's always the aqueous ions on the right. And the KSP usually is just the products in this case, because the reactants are usually always solids. So we never really include those in there. We do the same thing. So we still obviously take the coefficients like normal, if there are some coefficients. And there's really sort of, as we saw when we're kind of doing basic sort of KSP type problems, really two types of problems. One where you are actually asked to solve for the value of the KSP. And in those cases, you're usually given some type of solubility of the compound. It may be grams per liter, it may be molar solubility. Maybe any other unit as well, but whatever unit in terms of the solubility they give you, you do want to convert it into really the molar solubility, and then you could go into the actual molar solubility of each of the ions, and then into the KSP expression to really solve for it. If all you're given is pretty much the formula and the KSP value and asked what is the molar solubility, that is definitely the way where you need to do an ice table. And again, we do an ice table. As we've talked about, the kind of difference is we do use sort of S instead, and S is the molar solubility, which is I guess a fancy word for molarity, basically. So it is the molarity really of that particular compound and all its ions. You can make an assumption as well if you happen to have an initial concentration. And that was something that we did a number of examples on towards the end last time, sort of the effect on solubility. So remember that if you do have a common ion, that's going to shift the equilibrium to the left and really decrease the solubility of that particular solid. Remember that also pH can play an important role as well in terms of the solubility of a compound. Especially if you have some type of salt that involves OH minus or H plus, so maybe an insoluble base or insoluble acid. We did one where we sort of figured out the baseline pH of that particular guy, and that was like 10 point something. I think it was like 10.4 maybe, or 2. And again, if you sort of either raised or lowered the pH, it had an effect on the solubility. In one case, if you sort of raised the pH of that base that we were looking at, it would decrease the solubility because you basically were adding hydroxide to it. If we lowered the pH, that would increase the H plus concentration and make water, which actually would remove the hydroxide from that equilibrium, and that actually would increase the solubility. So as that slide said, and as we talked about, typically insoluble acids will be soluble in bases because that's basically going to remove H plus and cause the equilibrium to shift to the ion side. And insoluble bases are soluble in acidic solutions. Again, for the same reason, going to really make water and remove the hydroxide. The other thing that we also talked about in terms of affecting the solubility of an ion or a sort of soluble product or insoluble product is concentration of the ions that are in solution. So even though solubility rules may tell you that if you put these two ions together, you should get a solid that forms, the concentration is really important in terms of whether or not you would actually see that solid. And that's where we use Q and the KSP sort of comparison in that particular problem. And again, you could use Q versus KSP to decide whether or not you would get a solid or not, regardless of sort of what the solubility rules tell you. Again, if the concentration of those ions perhaps drops too low, you may actually not see the solid form as you would expect it to happen. The other thing that we finished up on in terms of KSP was the idea that you really can use KSP sort of to your advantage if you're trying to do something like what we do in qualitative analysis experiments, where we do selective precipitation and understanding the KSP and the concentrations that you need, for example, of a precipitating reagent. I think we looked at silver in that example that was trying to precipitate out the bromide and the chloride. You could use the KSP values to really figure out the minimum amount, like in that example, of silver that you would need to see the silver bromide come out versus the amount of silver that you would need in terms of its concentration to see the silver chloride come out. So it can allow you to do some calculations so you can selectively precipitate out certain ions and keep other ions really in solution. The last thing we sort of talked about in terms of KSP was the idea that if you are comparing two insoluble salts and they do break apart into the same number of ions, you could directly use the KSP value to help you determine which one should be more soluble and which one should be obviously less soluble. The one that has the greater KSP value would mean, because it's still a K value, you should have more products at equilibrium. And since products are aqueous ions, that would mean it would be more soluble. And the guy with the lower KSP means that it should have more reactants at equilibrium, and reactants in this situation would be more solid and it would be less soluble. The one time where you really cannot use the KSP values to directly compare two salts or multiple salts is if those salts do break apart into different numbers of ions. So if they do basically make different numbers of ions on the product side, you cannot use the KSP to directly compare those two. Any questions on any of that stuff? I think we ran through the last time. All right, so obviously, as we talked about also last time, this really does relate to those qualitative analysis experiments. We've done group 1, and I think group 3 and 4 is on tap for the upcoming weeks. After spring break, they got rid of group 2 altogether. Remember that these guys, as we talked about when we were talking about qualitative analysis, these are groups based on solubility sort of factors or properties. So again, basically group 1 is all those exceptions for chlorides, silver, right, lead 2, and mercury 1. Group 2 have very similar solubilities, group 3 as well. There are precipitating reagents, as we talked about, and group 2 and 3, it's actually sulfide is the precipitating reagent for those groups, but it is in different conditions. And this is what we were talking about earlier when we were talking about pH. For group 2 ions, you need it really acidic, like down to 0.5 in terms of the pH. And that will allow all those group 2 ions really the right environment for them to precipitate out. But that is actually way too acidic for group 3 ions, even though they're using the same precipitating reagent. And for group 3, as you will see, which I think that's the one we pick up with, you actually have to make it pretty basic to allow those guys basically to precipitate out. So again here, even though we're kind of using the same precipitating reagent, which is sulfur, the conditions play a really big effect as to whether or not those guys would precipitate out. And by controlling the pH, like we talked about sort of in those problems, you could also control how it will either precipitate out or not precipitate out. Group 4 and group 5 are sometimes comboed together. Group 5 has a lot of things that are soluble in everything, which frankly means you always end up with sort of flame tests, which we will do sort of those guys at the end. There are a few guys like barium and calcium, those guys, this could still be precipitated out. That's what you look like as you're doing it, obviously, and our flame test there. Any question on KSP? The last topic we're going to talk about here in this chapter is complex ion equilibrium. And a complex ion is really a metal in the middle. A lot of times it's a transition metal. And if you sort of remember when we're talking about salts, there are some metals that have a large positive charge that can go through hydrolysis. It's sort of a similar situation. We usually have a metal in the middle and a bunch of what are referred to as ligands that are attached to it. So for example, here, this is cobalt, and 4 chlorides, which is a really good ligand, makes this complex ion. And in a later chapter, you will know how to properly name that. Needs like this much of the page to write the entire name of it, but we will get to that a little bit in chapter here. But because this is an equilibrium, we could write an equilibrium constant, and this is still our products over reactants. So again, this guy here divided by the concentration of our cobalt, and just like normal here, we would take the 4 and have to take it to the 4th power to calculate the K. This is what is known as the KF. We could add it to our ever-growing list of K values now: KSP, KA, KB, KW, KC, KP, KF. Again, this class is brought to you by the letter K in this case. Now, KFs are really the equilibrium constant for complex ions. As the KF value increases, the stability of the complex ion also increases. And again, this is really still just the basic equilibrium constant idea. Obviously here, if we have a large value of K, that means we should have a lot of products at equilibrium. And in this case, product side is pretty much your complex ion that's being formed. So KF values, as we will see and sort of talk about, are a little different than KSP values. If you remember, KSP values are very, very small values. And that's because we mainly have reactants, which are solids. With the formation of a complex ion, the KF values are usually pretty big values. So they're pretty large values, which means the formation, as we'll talk about here, of a complex ion is oftentimes very much favored to occur because they want to come together really quickly. Here's a couple of examples. This is cobalt surrounded by 6 waters. And this is obviously a cobalt surrounded by 4 chlorides in this case, making both complex ions here. And obviously different ligands and sort of perhaps that are attached here gives us some different properties. So let's talk a little bit about ligands. Ligands, by the way, are our friends, which are Lewis bases. Yeah, and Lewis bases are things that will donate a pair of electrons. And that's why something like chloride, which is this, negative charge, something like water, which is H2O. That's good, I know that. All right, that's water. Something like ammonia. These are all really good Lewis bases because these guys are polar and have non-bonding electrons. And obviously something that has a negative charge pretty much gains some electrons, which means they have some electrons to give, and they make really good ligands. So when we look at the ligands, we sometimes also, our complex ions, we also sometimes will look at what is referred to as the coordination number. And the coordination number is the actual number of atoms that are bound to the metal that's in the middle of the complex ion. A lot of times it is a transition metal that's kind of in the middle there of those complex ions. So however many atoms are directly bound to it. So for example, here, our cobalt that we were looking up there before basically has 4 of these chlorides directly attached to it. The overall charge here is -2 because the cobalt +2, right? And each of these guys technically are -1, right? And that's how we get to our -2 overall charge for that ion. Now, in terms of the coordination number here, coordination number for this guy would be 4. And that's because there's 1, 2, 3, and 4 atoms directly attached to it. That's our cobalt with our water, and our cobalt would be attached to our water here, and it would be attached to the oxygen side. I'll just draw 1. And we have 1 water there, 2, 3, 4, 5, and 6. Now, in terms of the water, it is actually just the oxygen here that's attaching. So basically 1, 2, 3, 4, 5, and 6 would be his coordination number. Now, sometimes people get a false understanding of coordination number, and obviously we'll talk more about it when we get to that chapter a little later on in the semester. They think it's always the sort of subscript that you see next to like the ligands. And that is true in certain cases. There are different types of ligands. There are ones that are referred to as monodentate, or sometimes referred to as unidentate. And that's pretty much everything here that I drew so far. And what that basically means is for every molecule of your ligand, only 1 atom actually attaches to the metal. So there's actually just 1 sort of connection point between the ligand and the metal. There are certain ligands that actually can attach in multiple places per ligand. So for example, if you looked at another ligand, which is this guy here, give it the old college try drawing, like that, a little bit of that, a little negative there, a little bit of that, little negative there. This is our good friend oxalate. Yeah. Oxalate, when it is a ligand, it's what's referred to as being bidentate. And that means that the metal ion in the middle actually attaches to each of the oxygens in that particular ligand, which is why it's referred to sometimes as being bidentate, because you get basically 2 attachments per molecule, which means if I had 2 of these guys here, it would also attach here. That means in this case, although I only have 2 molecules of oxalate, which is C2O4 2 minus, the coordination number in this case actually would be 4. Yeah, and it would be 4 because there's 1, 2, 3, and 4 spots where it attaches. So although the formula may look something like this, if you solve the formula, I'll just use M for metal, C2O42. And again, you may go, okay, it's a 2, the coordination number is 2. Coordination number here would actually be 4 in this case, because for every 1 oxalate molecule that you put in there, basically you get 2 for 1 in terms of the binding to it. It obviously ties up the metal a lot better, right, than say a monodentate. And as we'll talk about as well, certain ligands are used as metal chelators because they can just like grab onto the metal in multiple places. EDTA, as we will see a little bit later on in a different chapter, can actually bind 6 places per 1 actual molecule of it. So it basically can surround a metal pretty well and stuff like that. Any questions on that? All right, so let's take a look at a problem that involves complex ion, and let's talk a little bit about how we go about working these type of problems. And it is a little bit different than some of the approaches that we take to other problems. So in this particular case, we're going to take 0.2 moles of copper 2 sulfate, and it's mixed with a liter of 1.2 molar ammonia. What is the concentration of copper 2? And we're just going to keep, for this example, all the volumes as 1 liter, just to keep the math a little bit easier. Obviously, that's not always the case, so we're just going to kind of do it on this particular one. So what we're looking for in this particular case is we would like the molarity of everybody together once they are mixed together. So in this case, because everything is 1 liter, we know that the concentration of copper in this case will basically be 0.2 molar. Again, that's basically 0.2 moles divided by 1 liter. In this example, gives us the 2 molar. In normal cases, if you mix 2 solutions together, a little M1V1 equals M2V2 action, right, to get the concentration of all those guys in solution. That is the copper 2 solution concentration, because copper 2 sulfate breaks apart into a copper 2 ion and a sulfate ion, which means the concentration of this guy and this guy will be the same. So that's how we get to just the copper 2 part. The ammonia here is 1.2 molar. So again, we're just going to assume that the total volume and all that's going to be 1 liter. So we're going to leave it as 1.2 molar. So we will do an ice table in this case. So initially here we have 0.2 molar. We also have 1.2 molar and 0 here. Now I'm going to do this ice table 2 ways and explain sort of the difference here of how we do it. If we did it like we normally did with x's, for example, this would be minus x, right? This would be minus 4x because of the 4 that's there, and this would be plus x in this case. So when we work these type of problems that involve complex ion, we look at the K value here, and this K value is a small value or a large value. This value is a large value. It's a pretty large value, to the 13th, right? Which means basically we make certain assumptions in these type of problems, and the assumption that we make usually is, because this is so big, all of the metal will end up in the complex ion. And again, that's a pretty safe assumption in a lot of these KSP type problems because the values are so large, even though it is a reversible reaction, it's almost like a one-way street kind of heading towards the product side. So it's almost like it's all going to the product side, but it is still a reversible reaction. So a little bit of it is going to come back the other way. So what that means is in this particular case, that we actually can use a number for the change part here. So much like what we do when we're doing sort of volume to volume additions, we know that the change here is actually going to be the amount of the metal in this case, which is copper. So I'm just going to do a second change underneath it, which is actually going to be minus 0.2. This would be minus, we still need to take the 4 into account, 4 times 0.2, and this would be plus 0.2. That means that when we get to equilibrium here, by using the numbers, I'm just going to kind of cross that guy out. That would give us none of the copper left over. That would give us 1.2 minus 4 times 0.2. 0.4 of our ammonia left over, and 0.2 of this left over. Any questions on the table? So one of the major sort of assumptions that we make when we do a KF type problem is we assume because the K value is so large, all of that metal, whatever it may be, should really end up in that complex ion and pretty much get all used up. So the question might be, if that is the assumption we make, why are we even solving this problem? We want to know what is the copper 2 concentration at equilibrium. So clearly, if the answer was going to be 0, we wouldn't have much work to do. And the answer here is not going to be 0. But the answer here is going to be a really small number. And it should be a really small number because although almost all of it is heading to the product side, it is still a reversible reaction, which means just a smidge of it will come back the other way. So you'll have a little bit of it that will sort of eke its way back the other way. So the second part of the assumption is when we actually do solve for the actual metal part, it should end up being a really small number. It should be almost like not much there at all. So what we do in these problems is, even though that we kind of zeroed out the copper, we're now going to call the copper X because that is essentially what we're looking for. And we could actually use the KF expression here to help us figure it out. The KF in this case would be our products divided by our reactants. And once again, do not forget that you still need to take that guy to the 4th power. Going to equal our 5 times 10 to the 13. So we're now going to put everything in our equilibrium line into our reaction here. So that is going to give us 0.2 up on top. That is going to give us the copper 2, which is what we are looking for. And that is going to give us our NH3, which is 0.4 that I need to take to the 4th power here. And that's going to equal 5.0 times 10 to the 13. So mathematically speaking, when you solve for the copper 2, basically what happens is these two guys switch places. Basically is what happens. You multiply the copper 2 to the other side and you divide the K value to the other side. And that would get you basically 0.2 divided by 5 times 10 to the 13. And that is going to be our 0.4 to the 4th will equal our copper 2 concentration in this case. So if we go and solve that, that's going to be 0.2 divided by 5 to the 13 divided by 0.2 to the 4th. Gives us here basically 2.5 times 25, 2.5 times 10 to the negative 12 as our copper concentration. Is that a lot of copper? No, it's pretty much all gone, right? So the assumption is good here. pretty much all of our copper in this case ended up in the complex ion. But again, because it's still reversible, a little bit of it made its way back, almost pretty much nothing. And again, if you got a really large number at this point, then you should look at your calculation. So you should really end up in most cases with a really small number there for the amount of free copper that is left over. Any questions on that there? Okay. So I think what we'll do right now is we're going to take a break. Yeah. And all right, let us continue on here and finish up. We just got 2 more examples to go, and then we'll talk about the rest of the stuff here. All right, so we did that KF example a second ago. So I'm going to let you go give a shot on this one here. We have our stepwise sort of formation. And by the way, just to where that thing is, for example, just to help you out with this problem here before you start it, is the idea that ligands, by the way, do come on basically one at a time. So although we look at the overall reaction, we'll just look at, say, that was cobalt plus 4 Cl minuses. And that gives us COCl4 2 minus. So although there is sort of 4 ligands, they actually do come on in a sort of a stepwise fashion, very similar to sort of how like the H pluses come off in an acid in a stepwise fashion. So really this sort of process here that we're looking at in this equation is really the overall reaction, and it does happen in actually 4 steps. The first thing that would happen is the cobalt would actually just pick up 1 ligand, and you'll get something like COCl plus. And there would be a K value for that particular one. The next thing that would happen is that guy right there would pick up another Cl minus, and that'll give us COCl2, which would also have a K sort of value for it as well. We call it K1, call it K2. The third ligand would come on to this guy here. And we'll end up with COCl3, also a -1. And lastly, that guy there will pick up our last ligand. Gives us COCl4 2 minus in this particular case. So ligands, again, really do get added basically one at a time. And a lot of times we can sometimes look at the overall reaction, which is our cobalt plus our 4 chlorides in this case. And we obviously get that just like any other sort of equilibrium reactions by adding these together. In this case, this guy and this guy would cancel. This guy and this guy would cancel. This guy and that guy there would cancel. That leaves us on the left-hand side, our cobalt and our 1, 2, 3, and 4 of the Cl minuses, giving us our COCl4 2 minus. Now, for KF in this case, because I added all those individual reactions together, what do I do with all those K values? I add them or multiply them? You do multiply them. So if you had a reaction like this where they gave you sort of the stepwise formation of that complex ion, and you're looking maybe for the overall K value, in this case, you would take K1 times K2 times K3. Got a lot of glare there, times K4 in this case, right? So you would multiply all those guys. So sometimes you'll be given in these type of complex ion problems the sort of overall reaction, like the guy in the box on top. Sometimes you may be given sort of a stepwise fashion, but they're all individually equilibrium reactions, which means you can do product over reactants for all those guys and use them like a the overall reaction as well. You could combine them and kind of get the overall K value if you needed to figure it out. So again, just an example here, ligands do attach basically one at a time, and you can have a K value for each of those. Any questions on that there? All right, yeah. Where did I get where now? Where did I get this guy? And this guy? And that guy? I got it by adding 1 chloride there, right? 1 chloride to cobalt will give me 1 chloride plus 2 minus 1 plus 1. And then that guy then picks up 1 more chloride added to that guy. And that gives me CO, Cl2 plus 1 minus 1 gives me no charge on this guy. And then that guy picks up the next one. That's why we now changed into a negative here, because it's a Cl minus added to a neutral guy. And then basically this guy picks up the last one. So that's what a step-by-step sort of process is. Sort of the product of the first one becomes like the reactant of the second one, and it kind of continues in that pattern. Other questions? Okay, now that I remember to say that, that's good. Let's try this problem here. Here we do have a stepwise sort of formation of a complex ion. We're looking for really everybody's concentration here along the way. In this case, we're not going to keep the volume constant. So we're going to mix 150 milliliters of 1 times 10 to minus 3 molar silver nitrate with 200 milliliters of 5 molar Na2S2O3. And that is the individual stepwise formation there. So give it a try, see what you come up with, and then we'll talk about it. Talk about how to approach this. So as I said, here in this particular one, we're given a stepwise sort of formation. So it might be helpful just to add those guys together to get sort of the overall reaction we're sort of dealing with. When we add this together, this guy right here and this guy right here will cancel out, and that will leave us an overall reaction of silver plus a couple of these S2, that's an S, S2, again, maybe not, S2O3 2 minus, going to our complex ion here, Ag, S2O3 2 3 minus in this case. Here. Now, in this case, since I did add it together, and if I did want the Kf for this guy, I again would take both of these guys and multiply them together, and that would give me 7.4 to the 8 times 3.9 to the 4th. Gives me sort of a Kf for this overall here. We'll call it 2.9 times 10 to the 13. First off, any questions on that? So in this case, I'm looking for a lot of things. So I'm going to look at the overall reaction to begin with. But to do that, I do need the concentrations really of these ions here after they are mixed. So that is going to be a little M1V1 equals M2V2 action. Our total volume here is 150 and 200, which is 350. So here, the source of silver in this case is going to be our silver nitrate. And that means that the concentration of silver would be, and you don't need to convert it to liters in this case because we're going to divide by milliliters. So 150 milliliters times the molarity, 1.00 times 10 to the minus 3, divided again here by the total volume of both of those guys mixed together, which is 350 milliliters. Again, the milliliters will cancel. That's going to leave us in molarity, which is good. That's going to be a 150, 1 to the minus 3, and divided by a 350. We'll call it here 4.29 times 10 to the minus 4 molar. Our source of the S2O3 2 minus ion is going to come from here. And we would do the same thing. A little M1V1 equals M2V2 sort of action. In this case, it is 200 milliliters of that guy times its molarity of 5, still divided by the total volume, which is 350 milliliters. Once again, those guys are going to cancel out. Going to give us 200 times 5 divided by 350. Looks like a 286 there, 2.86 molar. Any questions on how to get those concentrations? Again, the 350 is the 150 plus the 200 that was mixed together to get the 350. Questions on that there? Okay, so I'm going to start this ice table very much like how I did the previous one. I'm going to use the actual overall reaction here to start with because really I have all that information available to me. So that's what I'm going to start with. So we're going to maybe start with something here. There we go. All right, so we have the overall reaction, which is our silver and 2 of those guys. So we got our silver plus 2 S2O3 minus, giving us our Ag S2O3 minus. And at this point, we're going to use the initial concentration of the silver that we calculated on the previous slide there, which was our 4.29 times 10 to the minus 4. We're going to do our S2O3, which was 2.86 and 0. Once again here, because this is the formation of complex ion, we're going to make our first assumption, which is all of that silver in this case should end up in the complex ion. We saw actually the K value there was like to the 13, right? So we should make that assumption. So again, here we're actually going to use numbers. And the change here should be the amount of the silver ion in this case, as that is the guy that should get tied up. So there's going to be minus 4.2 times 10 to the minus 4. This is going to be minus. We do not want to forget the 2 that is there. So we got to do 2 times 4.29 times 10 to the minus 4. And this would be plus 4.29 times 10 to the minus 4. That is going to take us to equilibrium here. Whereas we make our assumption, all of the silver will zero out. For our S2O3, we will end up with 2.86 minus 2 times 4.29 to the minus 4. Gonna frankly give us 2.86 still. Yeah. And this will give us 4.29 times 10 to the minus 4 molarity. Any questions on that ice table? At this particular point, we actually just got 2 answers that we're looking for. We got the concentration of the S2O3 minus is 2.86 molar. We also got the concentration of our kind of overall complex ion, which is 4.29 to the minus 4. So we got the concentration of our overall complex ion here, which is 4.29 times 10 to the minus 4 molar. So off of this first ice table here, we were able to really calculate a couple of concentrations that we were looking for. There is still 2 concentrations out there that we are looking for. And the 2 concentrations that we are looking for at this point is the silver concentration, and it is this guy's concentration as well. So we're still looking for those 2. So there actually is kind of 2 approaches that you can take at this point. And I'm going to show you one way, and then obviously I will tell you how you could obviously go the opposite approach. So just looking at the results of this particular table here, I could see if I look at the second step here, I have this value from that table, and I also have this value from that table, which means that would allow me to use the second equilibrium step to calculate the AgS2O3 minus just by using that. Now, because it is an equilibrium step, it's an equilibrium constant you could write and an expression. So you could just use the second step here, not the overall reaction, the actual just second step in that mechanism. And that is what I'm going to do. So I'm going to take the second step here in that mechanism, which is this guy obviously here at the bottom. And I'm going to write the equilibrium expression for that, which would be the concentration of our product here divided by our reactant, which is this guy. And this guy here. So this equals 3.9 times 10 to the 4 in this case. And because I am only using the second step, I am making sure that I am using the K value that goes with the second step. So I don't want to use anybody else's K value. It is specific here. And that is also why here the S2O3 minus is not squared, because in that second step, there's only one of them. So there's no squaring that's here. Obviously, we didn't use the overall reaction. And we can do that again because at this point, we pretty much have all those numbers. So putting those numbers in would give us 4.29 times 10 to the minus 4. And I'm getting these numbers from, obviously, the equilibrium step here that I just did, divided by the concentration of this guy, which is what I'm looking for. And I also have the S2O3, which is 2.86. And that equals 3.9 times 10 to the 4. Again, mathematically, if you solve for this guy on the bottom, these two guys are going to basically switch places. And that would give me 4.29 times 10 to the minus 4 divided by 3.9 times 10 to the 4 times 2.86 would equal the concentration of AgS2O3 minus. So putting that into my calculator, I will get here 4.29 to the minus 4 divided by 3.9 to the 4 and divided by 2.86, going to give me a concentration for this guy of 3.8 times 10 to the minus 9 molar. So what I did here is really just focus on the second step of the sort of stepwise formation, and that allowed me to get one of the missing pieces that I needed. Any questions on that there? At this point, now that I have that guy's information, I actually could go to step number 1 here and solve for the silver concentration, because at this point, based on the one we just did, I now will have this guy's concentration and I have this guy's concentration. So that is going to allow me now to use, just like I just did, just step 1 to figure out what the silver's concentration is. So here, just like I just did, I'm not using the overall reaction at this point. I'm just using the step 1 part of it. And that's going to hopefully help me get there. So let's take a look at that. So looking at step number 1, which is basically this plus S2O3 minus. And one of those guys there. And this would be our K1, which had a value on the previous slide there, 7.4 to the 8. All right, so I'm going to write my K1 expression, which would be the concentration of my silver here, S2O3 minus, divided by the concentration of the silver ion that's free, which is what I'm looking for, S2O3 minus, and that equals our 7.4 times 10 to the 8. Once again, from our previous table and the one before that, we really have both of those numbers. So that number that we just figured out there was 3.8 to the minus 9. Divided by the silver concentration, which is what we are looking for. And this guy, I believe, is still 2.86, equals 7.4 times 10 to the 8. Once again, these two guys are going to swap spots. And that would give me 3.8 times 10 to the minus 9 divided by 7.4 times 10 to the 8, and 2.86 would equal my free silver concentration. And at this point here, we would end up with a number. And should this number be a big number or a small number? The amount of free silver ion in the solution should be really small, right? That's the second part of our assumption. First part is it all gets used up, but because it's an equilibrium, some of it's going to come back, and it should really be a really small one. And in this case, we get a silver concentration of 1.9 times 10 to the minus 18 molar. And I would say that that is pretty much small, yeah, and not very much there. So what this example illustrated is you don't necessarily have to use the overall reaction for all the questions. You can use each individual step because each individual step is an equilibrium sort of process. So you could use it to your advantage here to get all the answers that you're looking for. Question on that one there. Now, to tell you or show you just really quickly, the alternative approach to this is you could have, at the point where we were here with our overall reaction, you could have done what we did in the first problem, which was we could have put it into the overall reaction and solved for the silver first. So if we did that from the overall reaction, which is basically this plus a couple of these guys, gives us a KF of our product divided by our silver and our S2032 minus, which we will square in this case, as this is the overall reaction, right? So here we do need to square it because we are using this reaction here. And that equals our very first number there that we had, which was 2.9 to the 13. That's where we combined them, and we got that number right there. So 2.9 to the 13. So at this point from our very first ice table, we had this number and we had this number. And again, we could then call this guy X, kind of like what we did on the first problem here. And if we do that and put it in there, we will end up with, I believe, 4.29. 4.29 times 10 to minus 4 divided by our silver. And this would be 2.86 squared equals 2.9 times 10 to the 13. And once again, these guys will switch places. That will give you a silver concentration at this point of 4.29 times 10 to the minus 4 divided by 2.9 times 10 to the 13 times 2.86 squared in this case. And if I didn't screw up here, we should end up with the exact same number that we ended up with up on top. So just to make sure. 1.8 pretty much there with rounding pretty close. 1.8 times 10 to the minus 18. So again, we do end up with pretty much the same number there by going in that direction first. Probably because I rounded the 2.9 guy, I think. So you could do the end part first, and with the overall reaction, get the silver at this point. You then could go into K1 and get the same answer at that point. Again, just a little bit different with the rounding, but pretty much the same number there. Any questions on this one? So you could use the individual steps to do it. You could use the overall reaction. There's multiple ways you could do it. Again, because they're all equilibrium reactions, You could basically put the values in. Any questions on that there? All right, so we've looked at now a stepwise sort of formation problem for a complex ion. We looked at sort of a regular one. We're going to finish up looking here at sort of a combination actually of both things, KSP and KF coming together. So let's take a look at this one here together and talk about what's going on in it. So what we're looking for in this case is we want to calculate the molar solubility of silver chloride in 1 molar ammonia solution. So we have our KSP expression here, which is our silver chloride breaking apart into silver ion and the chloride ion. We have our complex ion formation, which is the silver plus the ammonia, makes our silver and ammonia complex ion. I'm going to add these together here. And when I do, actually the silver ion in this case will cancel out. And this will give me silver chloride plus some ammonia. We'll make some complex ion and some chloride. Now, if I want a K value for this reaction, is it okay to multiply a KSP and a KF together? It doesn't matter. The answer is you can. They're just K values. So same idea as when you did like Ka times Kb equals Kw. So even though they're different little subscripts, they're all ultimately equilibrium values, and you can multiply them together. So in this case, we would actually take these two and multiply them together to give us the K value for the overall reaction. And in this particular case, it would be 1.6 to the minus 10 times 1.5 to the 7. And that's going to give us a K value of 2.4 times 10 to the minus 3 in this case. Minus 3. Any questions on that? So now when we look at this problem, though, it's really kind of no longer a KF problem in a sense, because we have no free ions running around, no free metal ions. And we're actually looking for the molar solubility, which is more of a KSP type problem. So the way that we would want to approach this is actually as a KSP type problem, because we are looking for the molar solubility. So I'm going to rewrite this here. A couple of ammonias. I got it right there. Perfect. So we got silver chloride plus our couple of ammonias, giving us our complex ion and our chloride. And again, our K value there being 2.4 times 10 to the minus 3. So we're going to do an ice table here, and really the only thing that was given to us was we had 1 molar of ammonia. We're going to assume 0 this guy and 0 this guy. And because we are looking for the molar solubility, we're going to use our S's. So this is going to be minus 2S. This would be plus S, and this would be plus S at this point. That means when we reach equilibrium, we got 1 minus 2S, S, and S. First off, any questions on the ice table? And again, we're approaching more like a KSP type problem because we're looking at first molar solubility a little different. We actually do, in this case, have some stuff on the left-hand side there. I am not really putting anything in the silver chloride because it is a solid, right? So it will not go into the equilibrium, although we are going to relate it to this in just a second, but we're not going to really put any numbers. So this is going to go into our equilibrium expression, which is, again, our products. Divided by our reactants. And again, here we do need to square it, and we are not going to include this guy, which obviously is a solid. Putting those values in gives us basically S squared divided by 1.0 minus 2S squared is equal to 2.4 times 10 to the minus 3. If you look at this, this is a perfect square. Yeah, so big old square root perhaps on both sides would be the best move. And that would give you S on top. It'll give you one of these guys on the bottom. And I should remember to actually square root that guy on that side. So we're going to take the square root of 2.4 to the minus 3. Going to give us like 4.90 times 10 to the minus 2. We're going to multiply that to the other side. And that would get us S is equal to 4.90 times 10 to the minus 2 minus times 2. 9.8 times 10 to the minus 2 S in that case. We're going to combine our S's, so I'm going to bring my S back to this side. And when I do that, I'm going to basically get 1.10 times nothing, 1.10 times S is equal to 4.90 times 10 to the minus 2. We're going to divide this over, and we will get a molar solubility of 4.5 times 10 to the minus 2 molar, which is the molar solubility of silver chloride in ammonia. Any questions on that math there? So how does this compare to the molar solubility of just silver chloride, say, in water? We calculated it earlier, and I have that number somewhere. Where is that number? 1.3 to the minus 5. So 1.3 times 10 to the minus 5 molar is silver chloride's molar solubility in water. And we did that in an earlier problem. Which one is it more soluble in? It is more soluble here in the ammonia, a lot more soluble, right? To the minus 2 versus to the minus 5. You actually did this in group 1, where you had your silver chloride and your mercury chloride solids. You added ammonia, right? And the silver went into the solution. It didn't really disappear. It made that complex ion when you added the ammonia. And then what you did is you made it really acidic after that, right? To see the solid come back. When you made it really acidic, you pretty much freed the silver from the ammonia because you protonated it. And that allowed now the silver ion that was freed to find this chloride ion that was still floating around. And that's why you should have saw, obviously, the reappearance of that white solid when you did that part. So you actually did this part in group 1 analysis. When you added the ammonia, so silver chloride went away, added the acid, freed the silver ions back up, that allowed it to react with the chloride ions that were still in there, and you saw it come back to life there. Question on that are KF type problems. All right, that wraps up chapter 15.